Just a second, I need to restart my computer and I'm back.
I am the host now. Wow. Yeah, I'm not going to do anything with it.
Jesus Christ, Sammy, what the fuck?
Who wants to see more? Thomas, I know you think it's hilarious. No, who did that? Did you do that, Thomas?
Now where is he in the room?
It's so peak.
Oh,
Thomas,
boy.
did you do that? Did you delete it?
what is this game?
I wrote
Oh.
poo-poo in the whiteboard, and then Thomas deleted it before you could find.
You seem like you're very proud.
I took your screen. Okay, hopefully now my computer works. Hi everyone, like I said on the email, linear algebra will be a review session as well. Afterwards in calculus, we'll move on. The review session will work the same as calculus. I'll do a quick rundown of the course up until now, and then I'll ask you to ask me questions if you have some, and if you don't, then I'll solve some exercises from tests. Review session. Okay, so first the quick rundown of the course, linear. The first chapter we had was, second, it's loading, was fields. We studied the definition of a field, and then just a second, let it load. Tabs. We proved that anything times 0 is 0. We talked a bit about the modulo operations. Then we talked a lot about the complex numbers field. So all this was the first chapter, fields. And the second chapter was a linear system of equations. We learned how to solve a system of linear equations using a matrix, echelon form, reduced echelon form. Next, we study about the matrix algebra. How do we sum up matrices, multiply by a scalar, and multiply matrices by each other? Finding the inverse of a matrix. Then vector spaces, we talked about, we defined vector spaces and subspaces. We defined the bases using the span and linear independency. Then we did the משפט המימדים, which I don't think we gave a name to. And that's it. And last time we started and we did the technical part of finding the three spaces of a matrix, the row space, the column space, and the null space. And we defined the rank of a matrix. Yeah, okay. So what we have left by the end of the semester is linear transformations, but we shall not start it today. Today we will talk about what we've learned so far. So first of all, like I said, do any of you have any questions about linear algebra, something specific or a general subject?
For me, the last lesson or the last two lessons when we started like basis and span, and that part started to get confusing in how they are connected and how exercise look for that part of the subject.
Is there any specific question, or could you? Because I'll tell you why, because on the very last lesson, we've seen how to actually do the calculations, right? Up until then, it was pretty theoretical, and there could be theoretical questions about it. But in the last lesson, we actually learned how to find bases and dimensions to vector spaces using matrices. But then again, do you have anything specific or just in general?
In general, I haven't started the new homework. Nir sent us homeworks for both Infi and Linear yesterdays, but I haven't looked at them yet.
Yeah, obviously. Okay. So you say focus on the last part, and I'll try opening up subtests. Last time it didn't work out well because everything has linear transformation in it. But still, let me try for a couple of minutes looking at tests from mathematics and see if any questions rise up. And I'll use the question to talk about it. Okay, this is the matrix. Then A, find. Okay, let's look at this one. It seems interesting. Let's solve this matrix. It has to do with the last few lessons. So you are given a matrix A, and in order not to waste the student time, we've calculated for you A squared and A cubed, meaning we actually did the matrix multiplication. And the first question is to find a basis for the null space of A. So that we know how to do. The next few questions are a bit more interesting, and we'll do them one by one. But first of all, we need to complement the basis for the null space of A into the null space of A cubed. So how do we complement? Do we find extra vectors to be the base for a larger space? We will see. Section C, we need to find a base to a sum of two subspaces, and in the fourth section, fourth part, we need to find a vector in the column space of A, which is not in the column space of A squared. So basically, it all has to do with subspaces and bases and whatnot of matrices. And here is a question, and we need to see how the material that we studied comes together in order to actually answer these questions. So I think that's kind of like what Thomas wanted. So the first part of the question is the easiest, to find a base to the null space. I'll remind you, and remember, in order to find bases to the row space of a matrix, the column space of a matrix, and the null space of a matrix, we perform Gauss elimination. And then for the row space, I'll tell you by heart, we take the rows different than 0 in the echelon form. For the column space, we take original columns from the matrix where that matches bounded variables. And for the null space, we solve the homogeneous system. That's what we need here. So we'll start with the matrix and we do Gauss elimination, and then we'll see where we go from there. So the matrix is -1, 2, 1, 1. Two minus 2, 3 minus 2. 2, 3 minus 2. -1, 1, -1, 1. And -4, 5, -3, 4. Hopefully I did not make any mistake there. So we do Gauss elimination, and if at any time you have a question, I welcome you to ask it. So R2 plus twice R1, R3 minus R1, and R4, row 4, minus 4 times row 1. These three operations will cancel out these two, this -1 and this -4. They will all become 0, and that's the way we perform Gauss elimination. Then we'll go to cancel these out, and then these, and that, and that. So, -2 times, +2 times. So 0, -2 plus 4 is 2. 3 plus 2 is 5. -2 plus 1 plus 2, sorry, that's 0. Next, R3 minus R1. This is 0. This is -1. This is -2. This is 0. And minus of 0, -3, -7, 0. Okay. Next, we need to cancel at this column. We prefer the 1 to be on top because it's easy to cancel using the 1. So the next operation I will apply will be to switch the second row with the third row, just so I'll have the 1 there. It's -1, but that doesn't really matter. So we'll have -1, -2, 0. And here there will be 2, 5, 0. And now we can R3 plus 2, R2, R4 minus 3 times R2. And we get this plus 2 times, so 0, 1, 0. Here we get 0, -1, 0. And next we can add the third row to the fourth row. Yeah. 0. So first of all, I will stop for a second. What did we get here? What form is this?
That's echelon, yeah.
This is echelon, but not reduced echelon.
Yeah.
And we want the reduced echelon form because we're looking for the actual solutions. We were asked to find a basis for the null space, meaning the solutions, not just the dimension. The dimension, by the way, is 1. We have 1 free variable. The null space of A is 1-dimensional. There is 1 vector in the base. We need to find it. But in order for that to happen, we need to find the echelon form. So first of all, we will make sure the pivot elements are all 1s. They're almost 1s, they're negative 1s, but let's make them actually 1. So this is 1, -2, -1, -1. This is 1, 2, 0. And now we can cancel these 2. And afterward, we will cancel that 1. So of R2 minus 2 times R3 and R1 plus R3. And we get here, because there are a lot of zeros, it's a bit easier now. And this is 0. This is 0. And lastly, we need to nullify the -2 there. So we take R1 plus 2 times R2, and we get the reduced echelon form, which is 1, 0, 0, -1, and that's the reduced echelon form. During the test, you don't have this tool, but during class, I can put it in the website and make sure I made no mistakes. So I will do that. I'll open the matrix calculator. And I go to system of equations calculator. And I plug the numbers here, which are the original one. So let's copy it from the original question. -1, 2, and 1. 2 minus 2. 3 minus 2. -1, 1, -1, 1. And -4, 5. -3, 4. And solve by Gauss elimination. So he got to here. Can I get it? Looks the same. I wonder if I can, no, it doesn't give me the reduced echelon form, just the row echelon form, but it's the same. You see, we have the 1, 0, 0 here. And if I'll turn this -1 into 1, this 2 into 1, this half into 1, and cancel these 3, it's the same as we had. Okay. So it seems fine. So what is the next step? After I find the reduced echelon form, we look at the pivot elements, which are, in this case, the one here, this one over here, and that one over here. These are the pivots. Sorry, these are the pivot elements. So we look at the pivot elements and the columns they're at. So there is a pivot element in the first column, in the second column, and in the third column. That means that the first, second, and third variables are bounded. What about the fourth variable? It does not have a pivot element in this column, therefore it is free. And what do we do with free variables? We plug in parameters into them. We now substitute W, the fourth variable, let's call it W. W equals T. Then X, what does X equal to?
T.
T. And what does Y equal to?
0.
0, and Z equals to 0. Therefore, the null space of this matrix are all the vectors of the type T, 0, 0, T, such that T is a real number, and that is T times 1, 0, 0, 1. And taking this vector and multiplying it by T is just the same, by definition, as taking the span of this vector. This vector is a one direction, like we said, Backstreet Boys, but not Backstreet Boys. And this is a one direction, and when you multiply it by a scalar, you have nothing to add it to. So you can just multiply by a scalar, and when you multiply by a scalar, you get an entire vector space. That's the span. So the null space of A is the span of this vector. The basis we found for the null space of A is 1, 0, 0, 1. And the dimension of the null space of A is 1. I think no one asked me to, but I still wrote it. It just asked for a base. But in order to find dimension, you just need to be able to count. The dimension is the number of elements in the base. So the bases here have one vector, which means the null space is one-dimensional. Any questions so far?
Yeah.
Yes,
So,
Sammy.
so the answer to this question is the span of 1001. That's the basis.
Come again, I didn't hear it.
But my mic isn't that good. The answer to this question is
Yeah. Yeah, the base. That's what I'm saying. They asked to find the base. The base is this set. A base is a set or a sequence of vectors. In this case, it's just one vector.
so would we write B of NA it equals and then a vector?
Where?
Hang on, let me write it in the
Come again, I didn't hear you that well.
wait, hang on.
Sure.
Is that correct?
What is correct? I hear you well.
What I just messaged on the chat.
I'll look at it. I didn't see it. Okay. So B, what is B?
The basis? Is that not how we
Basis of. Yeah, okay, fine. I never used this notation, but yes. Yes, that's what I wrote in words. The
Okay, fine.
basis of N of A is this. I wouldn't write it the way you do. It's mathematics because we're not allowed to say the basis of. There are many bases of, right? But this is one of the bases. But yes, and that's a base for N of A. Okay. Next step, we need to complement a base or a vector space into a larger vector space. Why is this larger? If a vector nullifies A, then it must nullify A cubed because I multiply by A 3 times. If by the first multiplication we got 0, obviously after we multiplied twice again by A, it's still 0. So the null space of A cubed includes the null space of A. And we need to complement the base we found to a basis of the larger vector space. So what are our options? And I wish to write. Next, it is easy to prove that the null space of A is included within the null space of A cubed. Take it as an easy exercise to make sure you know what you're doing. Therefore, we can complement any basis of NA into a basis for NA cubed. Why? Because that was part of the theory that we learned. We say that if we take a basis for the null space of A, the lesser vector space, and if it's not as a basis for the larger vector space, then there is some vector in the vector space which is not in the span of the bases we have so far. Therefore, when we add it, it will remain linear independent, and then we can add more and more. That's how we've proved that any finitely generated vector space has a basis. We never used it in a technical way, but in theory, we use that argument. So how do we do it in general? We will find a basis for this space. If we are lucky enough, it will already include the basis from the first part of the question. However, if it doesn't, we'll need to do something that I will show you. So we'll see what's happening. But for now, I'm not sure where the calculation will take us. So first, we find any basis for the null space of A cubed, and then we'll see. And then we will see what to do next. So, like I said, they calculated for us the powers of A, which is rather nice of them. Tomas, you have a question?
Yeah, no, I just wanted to ask, when they give you or when you have a matrix and you are asked to calculate the null space, can you
Yes.
also calculate the null space of the transformation, the transposition, and it's the same?
No,
No,
not at all. Not at all.
Okay.
Transposition is a whole other matrix. So we'll take A cubed. I won't even copy it. I'll just take the reduced form. It's rather easy. I'll write the operation I did. It's R4 minus R1. R4 minus R1. Look again, Y. This is where, wait, this is A cubed. The first and the fourth row are completely equal. So I'll copy it after the Gauss elimination, short Gauss elimination process. So we get the matrix, ampersand. And what was the row? It was minus 1, 1, minus 1, 1. So it's minus 1, 1, minus 1, and everything else is 0. Just to make sure they are not inventing it. Put that in A. No, I can't move it to the matrix calculator. Oh, I can. Okay, put that in A. Without the last. No, it's not what I wanted. Put that. Can I just remove? I don't think I can. Let's see, just a second. No, it doesn't allow me to. Okay, I'll just write the matrix from the start. So it's written here. Minus 1, 2, 1, 1. 2 minus 2, 3 minus 2. Minus 1, 1, minus 1. Minus 4, 5, minus 3, 4. And now I can calculate A squared. It's that matrix. Let's see if it's the same that is written on the test. Yes, that's exactly that. And if I'll ask it to calculate the third power, yeah, that's exactly what's written in the test. The reason I did it, so you don't think there is no connection between the three matrices given in the questions. It's really A squared and A cubed. You can calculate the the product. The reason we did it on the test is so that no students will have calculation errors in calculating A squared and A cubed, and then because these are rather large matrices, and that's not the point of this specific question. But you're supposed to be able to do that. In any case, we're here. That's almost a reduced echelon form. I'll just take minus R1 to actually be a reduced echelon form. So that's 1, minus 1, 1, minus 1. And that's the reduced echelon form. This, excuse me, is a pivot element, and it's the only one. Therefore, X is bounded, yet Y, Z, and W are free. So plug in y equals t, z equals s, w equals r, then what does x equals to?
It's minus t plus s minus r, or is it the other way around? Because it has to be 0.
It's equals 0, so that means x minus y plus z minus w equals 0. When you take it to the right-hand side, it will be plus t minus s plus r. Agreed, Thomas?
Yeah.
So the null space of A cubed is t minus s plus r, comma t, comma s, comma r, such that t, r, and s are real numbers. That is, hold on to your hats, t times 1, 1, 0, 0 plus s times minus 1, 0, 1, 0 plus r times 1, 0, 0, 1. And such that r, s, and t are real numbers. And that is the span of how many vectors?
3.
3, exactly. Because now you see each vector is multiplied by a scalar of your choice, any scalar, and the 3 results are summed up together. That's a linear combination. So that is the set of all linear combinations of these 3 vectors, 1, 1, 0, 0, minus 1, 0, 1, 0, and 1, 0, 0, 1. Luckily, that's what I was talking about, whether it will happen or not. This base already contains the bases for the null space of A. The basis for the null space of A was only the set with only this vector, and then the basis we found for the null space of A cubed includes that vector and adds a couple of more. So the question again was a complement, complete the base from the previous section to the basis for the null space of A cubed, and that's exactly what we did. We found a complement to the basis we found in the first part of the question, to a basis for n cubed. So the basis, like Sammy said, B of the basis of the null space of A cubed is, it's not the basis. The basis we found, that's a correct statement. So the basis we found is this set over here. And even though no one asked me the dimension of n of A cubed, what is it? What's the
3.
dimension? 3, exactly. It's the number of vectors in the base. So the dimension is 3. Any questions up until now?
Yeah. Can you just, I was following along with the working out, but I kind of didn't hear the beginning of the question of what we were actually trying to work out.
Well, I didn't understand anything. Do you want to write it and in the chat, and I'll read it and I'll answer? The voice doesn't come out too clear.
Can you hear me now?
Yes.
Okay, sorry, my computer mic is really bad. I wasn't following. I was following the working out. I didn't hear the beginning of the question of what we're actually trying to work out. Could you just go over it?
Yeah. Section B here.
Right.
Complete the basis from the previous section, Misseif Aleph, to a basis of the null space of A cubed. Why does that make sense? Because the null space of A is contained within the null space of A cubed. It's a subspace.
We
So if
proved that.
I kistachti, if you know in Hebrew what it means. I said it's easy to prove that. If you wish to, I will, but look at the screen, Sammy. I wrote, it's easy to prove that the null space of A is contained within the null space of A cubed.
Well, that's something. Is that something that we need to know in order to answer the question, or is that just?
It's obvious from the question. If it wasn't the case, then it's impossible to follow the instructions. Because say complete the base to the base for the larger space. If it wasn't contained, you could never complete it, right? But you do need to be able to prove that statement. It's like I said, it's rather easy. I told you by heart why is it correct, but I suggested you do it as an exercise to see that you can. But again, in this question, you were not asked to do it. I'm saying this is implicit. If you were asked to complete a basis to a larger basis, then the vector space must be contained within the larger vector space. Otherwise, the very question is impossible. Agreed?
Okay. Yeah.
So, and the third section, the third part of the question, we need to find a basis for the sum of two vector spaces. And I'll remind you something that I didn't prove in class, but I did give you as homework in class. Remember, and I do need it now. Do I need if? Yeah. If V is, let's write here, sorry. If U is the span of the set A, and W, and W is the span of the set B, then U plus W is the span of the union of A and B. So why does that matter? We are asked to find a basis for the sum of two vector spaces. So what we can do is find a base for one vector space, then find a base for the second vector space, then union these two sets. That is a set that spans the sum, but it doesn't have to be a base because there could be linear dependency there. Then we can strike out the linear dependent vectors by putting them all in columns of a matrix and doing Gauss elimination. So that's one way to go about this question. But also, That's something that I didn't say explicitly, but also one can prove that the column space of A cubed is contained within the column space of A. That's a less trivial fact to know, but still I urge you to do it as homework. And that simplify the section of the problem. Why? Because if one space is contained within the other, then by closure, what is the sum of the two vector spaces if one is contained within the other?
Just the bigger one?
Exactly. Therefore, by closure, and C of the closure property, the sum is simply the bigger one. Meaning that noticing that can help me, instead of also I say then again, okay, because it's something else we can do. Wow, Sammy, it took me a while to understand that you are twice here. So who is this new student? You look completely different from this angle. Okay, so no, you
No, it's better this way. So you can see
should
my
have
you can see my face from my computer's point of view.
yeah, but I can't see up your nose the same.
Oh,
from
I
that
didn't realize.
angle.
I didn't. That's so embarrassing. I didn't realize my video was on there. That's awful.
Yeah, okay, no, funny.
That's so bad.
Yeah. No, but I kept thinking, who is this student? I don't recognize him. Funny. Okay. In any case, in any case, this is the long way to go about the question. This is the easier one, and a lot of times we do that in exams to make sure who is thinking before he acts, then he wastes less time than other students. So surely that was the reason behind this question. I probably knew it as being one of the lecture of this course, but who remembers every nook and cranny? But that things like seems sorry, like the point here. But however, that's another important thing. We need not guess since we've opened up, it was this 20 linear, yes. We can open up the solution. All the tests here has solutions, and then yes, and then we can see, first of all, the answers. Here they proved why is it contained, and they found the basis. And here you see, first thing they claim, the column space of A cubed is contained within the column space of A. They actually proved it. You're welcome to read it later. And then they say, oh, then obviously the sum is the bigger one. They didn't say using closure, but my way was easier, I think. But this is more explained better. So in any case, yeah, they wanted you to notice it instead of doing the hard work that I suggested before. Okay, so in order to find the column space of A, we actually finished the question. Why? Because we already did Gauss elimination for A. And remember that the first three columns contain matches, the bounded variables. And the algorithms say, just take the columns that matches bounded variable from the original matrix. So all I have to do here is write the answer. I did all the calculation. I just need to write the answer. We have seen in section Aleph that the first three columns of a match bounded variables. Therefore, the first three columns of A itself, not the echelon form, A itself, form a basis for the column space, i.e. the column space of A is the span of the first three columns, which were... Scrolling won't work well. I'll go to the question here. So it's -1 to -1, 4. Then 2 minus 2, 1, 5. Then 1, 3, -1, -3. So that is the basis. The basis we found for the column space of A plus column space of A cubed, which is the column space of A, is this set, and the dimension is ring. Okay?
Just a question, when we calculate the column space of a matrix that we already got, do we have to flip it or just leave it as is?
No, we never flip. We never flip. If
Okay.
you've seen anyone flip it, it's because it's stupid. No, I'm half kidding. But you flip it if you wish to work on the rows versus the columns, or vice versa. But why am I saying this is stupid? Because I've taught you an algorithm to find all spaces with no flip. So what you're doing is saying, I know just how to find a row space, or I know just how to find a column space, so I'll flip it and do it twice. But I taught you in class how to do both, so it doesn't make sense to actually do it. Why does it happen? Because different people have some, I don't know, not fixes as to go on use one algorithm. And I don't think it's the best case, but it is possible. But you'll almost never see me flip a matrix in order to find a space.
So in this case, you just use the pivots and just selected the lines.
Yeah. I can't think of one place where I do flip. If I want to find the algebraic form of the vector space, I can only do it in columns. And in this case, I do flip the matrix. Okay, that's a case I thought of, that I do have to flip the matrix, because I only have an algorithm for that in columns. But just find bases, you have an algorithm for all three without any flipping. Okay. So, question number 4. We need to find a vector in the column space of A, which is not included in the column space of A squared. And there are a few ways to go about it. sometimes when I see such a question, I wish to dive into the theory and show you, like before, how to solve any such question in general, but it's not a good strategy to solve a specific question. And now I wish to show you how to solve questions. So I won't do the smartest thing, and maybe afterwards, if you want, I'll show you a smarter solution that I will show you now. So for now, the so-called stupid solution or dumb solution, I'll find a basis for a cubed, a squared, sorry. I might need to do this step anyway, to be honest. And then after I have the two bases, I will give you an explanation as to how to find a vector which is no part of it, and it will has to do with the actual basis that we'll find. So we need to find a basis for the column space of a squared. This time we need to go the distance. We need to do the work because a squared is a matrix that we did not Gauss eliminate at all. It's a whole new matrix. We need to work with it by itself.
Matrix.
What's that mean?
No, I was just the what's it called? The Little Mermaid.
Yes.
The song A Whole New World.
Yeah.
Oh wait, no, sorry, that's not Little. Is that? That's not. No, that's
No,
that's Aladdin. That's Aladdin. My bad.
Aladdin, yeah.
Aladdin. No, you said A Whole New
Yeah.
Matrix, so I was
Yeah.
thinking that.
Okay, that's okay. Next time you can keep it to yourself. No, I'm kidding. Okay. My wife is into musicals, so I hear all these things all the time. Okay. So a squared is, I'm just copying it now. Matrix, do this, ampersand, and it is 0, 0, 1, 0, minus 1, 1, minus 1, 1, 0, 0, 0, 0, 1 minus 1, 2 minus 1. So I'll skip to the echelon form as to not to waste any time. And we get to we get to 1 minus 1, 0 minus 1, 0, 0, 0, 0, 0, 0, and surprisingly 0. Okay. So this is the reduced echelon form. We didn't actually have to find a reduced because we were not asked about the null space of this matrix, but I did it nevertheless. We have two pivot elements here. The first one is in the first column, and the second one is in the third column, which means the bounded variables, I'll write pivot elements. The pivot elements are in the first and third column. Therefore, we take the first and third columns, from the original A squared matrix. So thus the column space of A squared is the span of 0, minus 1, 0, 1, 0, minus 1, 0, 1, and the third, it's easy to see here, by the way, that the second column is just a multiplication of the first one by minus 1. It's completely linear dependent. And the third one is 1, minus 1, 0, 2. 1, minus 1, 0, 2. So we've calculated the dimension of the column space of A squared, meaning the rank of A squared is 2. But we were not asked this. We were asked to find an element of CA. We were asked to find a vector of the column space of A, which is not in the column space of A squared. Now, looking just at the basis, and the base we found for C of A is, where is C of A? Did we find, yeah, here is this. And the base we found for C of A squared is this one. And now it becomes interesting because does any one of these three vectors contained within this set? Is this vector here contained within this set? Is it one of these two vectors? It's not a trick question. Is one of these two vectors equal minus 1, 2, minus 1, 4?
No.
No. But that does not mean, note, while clearly minus 1, 2, minus 1, 4 does not belong to this set, to the base, it does not mean that this vector is not contained within the span of this set, which is C of A. So my question is not C of A squared, sorry. My question is not which vector is in this basis and not in that basis, but we need to find someone in C of A, and we can choose an element of the basis. That makes sense. But we need to choose one that it's not, that you cannot create from these two vectors. And that might be a bit of work. How can we know? How can we tell? How can we tell whether it is contained or not? We ask ourselves, does there exist scalars such that minus 1, 2, minus 1, 4 is A times 0, minus 1, 0, 1 plus B times 1, minus 1, 0, 2. That's the question. Can I create this vector. Is this vector contained within the column space of A squared? Is it a linear combination of these two vectors? And we'll have a linear system of equation we can solve. This gives rise to the following system of linear equations. I'll write it up. So the variables are A and B. So A times 0 plus B, that's B, equals -1. Next, minus A minus B is supposed to equal 2. Next, A times 0 plus 0, oh, that's kind of easy, has to equal -1. How do we call such a line?
Contradiction line.
Contradiction. That is that system obviously does not have a solution, therefore indeed on their door. Therefore indeed, and the vector -1, 2, -1, 4 is not contained within the column space of A squared, yet it is contained within the column space of A. That's where we took it from. So that's the answer to the question. And now I have an educated guess that will be the exact answer. There are many solutions, right? I choose randomly the first vector, or someone else might have chose the first vector to the right or the center one or anything else, but I have a hunch it will be the same in the answer to the test. Let's see. They gave a rather elaborate answer. They say every linear combination will always have 0 as its third coordinate. That's for every vector whose third coordinate is not 0 will do. And then they say one might notice that this is the case for all 3 vectors here. So basically they say you can choose any one of them and it will work. That's just the same. Okay. Any questions so far? So let us take our break until 2:30 and then we'll continue. If you have questions, we'll do them. Otherwise, I will keep solving questions for the exam. See you in 2:30. Is anybody here? Hello, there's Sammy. Okay. So let's solve the second question as well. It seems right up our alley. Copy it first. So we have the matrix A, and we have the two vectors B1 and B2. All are described using some parameter A. And we are asked for which values of A does the system A cubed x equals B1 does not have a unique solution, meaning either there are infinite number of solution or no solution at all. Something similar for A squared and something similar for A. So the worst the worst way to solve this, which I won't do because it's does not make sense at all, the worst way to solve this question is to calculate A squared and A cubed in general. What does it mean in general? For a general A, value of A, value of the parameter of A. And I'll put it through the computer to show you why it would be such a horrible idea. And afterwards we'll need to decide together. I'll give you a chance what to do. So I'll just plug in the matrix. It's -4, 0, A plus 2, A plus 2, and this is 6A minus 4, 2 minus A, 4 minus 6A, minus 2A minus 4, 0, 3A plus 2. And now raise it to the power of 3, and that's the way it looks. So this is not what you want to do, okay? Getting polynomials in the third power and start doing the calculation here, it will be horrific. So what can we do? Does anyone has a smart idea as to how to be able to go about it without doing the horrible calculations?
What are we trying to do again?
Find the number of solutions to this system of equations. A cubed x equals B1, A squared x equals B2, and AX equals B2. These are a linear set of equations. You have the matrix A, and you have B1 and B2. So the brute force idea is to, let's even look just at the first part, right? Just the brute force idea is to calculate A cubed and solve a system of equations. But A cubed look like this. Okay, the question is for which values of A does the system of equations a cubed x equals b1 does not have a unique solution? So you need to find the number of solutions. You have the coefficient matrix, which is horrible, and you have the constant vector, which is reasonable. Okay. And I claim that doing it with this matrix is not a good idea.
Well,
And
if it doesn't have a unique solution,
yes,
then there must be a contradiction, right? Or no contradiction.
Yeah.
Like you must have at least one line that doesn't have a pivot.
yes, but then again, you don't wish to do Gauss elimination on A cubed. Right? The way you said it, it's this brute force solution. Do Gauss elimination, and after I do Gauss elimination, the answer is really easy because, like you said, I'm looking for the pivots. But like I said, for section, that's why there are three sections here. For Bet and Gimel, that's for Gimel, it makes completely sense. For Bet, since it's only A squared, it's probably not as horrible as A cubed. Let's look at it. Still not great, but I can work with it. Okay, maybe.
Can we use the theorem that we stated earlier?
Which one?
The thing about the column space of A included in the column space of A.
It is possible. It is possible. It's not what I've. It's not what I'm thinking about, but it might work. But there's another subject that you're missing. In order to find, there is a theorem about when does a system of equation have a unique solution. What can you say about the coefficient matrix that promises a unique solution? You remember by any chance?
There can't be any zero rows in its
Yeah, but that's not the theorem. That's like the brute force way. There is an implicit theorem. So I'll tell you. Remember that if the coefficients matrix is invertible, then the system has a unique solution. Then A cubed is invertible if and only if A is invertible. So that's the smart way to go about it. And if we'll just invertible, if we'll just make sure when A is invertible, then we will know when there must be a unique solution, and then we'll take the other action, other possibilities. And if you look at the first section, we are asked where there is no unique solution. On the second section, we are asked where there is no solution at all. So again, if the coefficient matrix is invertible, there must be a solution. And for the third one, we're looking for an infinite number of solutions. So in all sections, all parts of the question, we need to exclude the cases when which the matrix is invertible. And my educated guess is there are only finite amount of cases where the matrix is not invertible, and then we will remain with this question only for these cases, which will be rather easy. And let's see if I'm correct. So instead of answering this question, we will first ask ourselves for which values of the parameter A is the matrix A invertible. And then we'll move forward. So, and I didn't copy A yet, so I'll do it now. And how do I find, and Sami, in order to find if the matrix is invertible, you will look at something similar, whether you get rows of zeros when you do Gauss elimination. But
close.
Yeah, but yeah, you were. But what I'm saying is that the trick here is to think about invertibility, which allows you, instead of checking A cubed, to check A itself, which makes the Gauss elimination much, much easier. So, A is matrix.
If A cubed is invertible, does it imply A is, or does it only go the other way?
Yeah, if and only if. If and only if.
Right.
So, -4, 0, A plus 2. Six A minus 4, 2 minus A, 4 minus 6A. Do it from the test itself, so we won't make any mistakes copying. Where is the question? That's the question. So -4, 0, A plus 2, 6A minus 4, 2 minus A, 4 minus 6A, 2A minus 4, negative 2A minus 4, 0, and 3A plus 2. So we put that alongside the identity matrix and start to do Gauss elimination to see whether or not we can get to identity matrix on the left, or whether on the left we'll get a row of zeros. So that's 1, 0, 0, 0, 1, 0, 0, 0, 1. Actually, I'm not sure if what I'm doing is not a waste of time, because I'm actually calculating the inverse as well. I think but I think it will help me at the end. I could just find the echelon form of the left-hand side and check whether there are pivots at any column, and I will know whether it's invertible or not. What I'm doing now is actually calculating the inverse, and it will help us. Will it help us? I think it will help us. We will actually, no, it won't help us, since I can use it, but it will be confusing. No, I won't. I think it will be a more confusing solution. I'll just do Gauss elimination. So, and first of all here, let's cancel the 4s here and here. I think it will be helpful. So R2 minus R1 and R3 minus R1. Hopefully that will be for the best. And so this will be 0. This remains 2 minus a, and this minus this. So minus 6a minus 8 minus 7a, 4 minus 2 is 2. R3 minus 1. So here the negative 4 is cancelled, 0 remains 0, and here 3a minus a is 2a, and 2 minus 1. So here we have 2 a's. By the way, I think the solution that we were going for was using determinants, but you did not study determinants or will not study determinants at linear 1. So I'll solve it without determinants, although it would have made the calculations a bit simpler. And it's not much simpler, but a bit simpler. And here I'm so tempted to divide by a, but usually my advice is not to do that. Yeah, I don't have to. Okay. So first of all, I'll cancel this 6a over here by doing R2 plus 3 times R3. And we get 0. This remains the same. And here, 2 minus a. Oh, that's nice. That went well. And now we need to cancel this one over here. So first of all, I can divide by negative 2. So, and minus half R3. And I can also divide by negative 4 the first row. So it's minus a quarter R1. And let's see what we get. So this is 1. This is minus a quarter of an a minus half. And here we get a and minus. So the last operation will be R3 minus a times R1 as to cancel this a over here. And we get here 0. This is also 0. And here minus a plus a squared over 4 plus half a. Great. So this will be invertible. The matrix will be invertible if and only if 2 minus a is different than 0 and a squared over 4 minus half of a equals 0. And that means that a not equal, different than 0, sorry. Different than 0. So A must be different than 2. And I multiply this by 4. A squared minus 2A must be different than 0. A times A minus 2 must be different than 0. All together, A is invertible if and only if A is neither 0 nor 2. So, since if A is invertible, so are A squared, A cubed, and the system AX equals B, A squared X equals B, A cubed X equals B, will all have unique solutions, and the answer lies only within the cases where A0 or A is 2. So instead of trying to solve it brute force on a horrible huge matrix with parameters, we can, well, the size of the matrix does not change, but a matrix with very complicated algebra using parameters, we can simply plug in 0 and 2, and then the worst case is solving the question twice. And there are more smart things to say, like the connection between B and C, Bet v'Gimel, since like Sammy said, it has to do with the column span, but I don't think I will even present it. I think it's easier just to solve it with 0 and 2 twice. So, but I will need to be able to calculate A cubed in these cases. So, yes, let's do that. So, first, I'll write something of what I said. There might still be a smarter path to this question, but we will plug in these suspect values of A and brute solve the question. So first, for A equals 0, let's see what happens. What is A? So I'm copying A. And it equals to -4, 0, 2, -4, 2, 4, and -4, 0, 2. And I'll start with C. We wish to start with Gimel. Start with section Gimel. And we need to solve this coefficient matrix along with the constant column of constants where a equals 0, but we need B2, I think. Let's see. Yes, AX equals B2. So B2 is this. With 0, it's -4, 6, -5. -4, 6, -5. And that is an easy question to find. The question was, who remembers, for which values of A does the system has infinite number of solutions? So we'll do it twice, once with 0, once with 2, and we'll find whether for one of these options there is infinite number of solutions, because all other solutions have all other values of A have unique solutions since the coefficient matrix is invertible. So, let's reduce this matrix. R2 minus R1, R3 minus R1, and we get 0, 2, -2, n. Here, 0, 0. That was rather easy. -1. What can you tell me about this specific case?
It's a contradiction.
There are no solutions. Definitely not infinite number of solutions. Now, I thought of plugging in A and going throughout. I'll do it the other way around. I start with the safe Gimel, which doesn't make me calculate the powers of the matrix. So we'll start with the section Gimel for A equals 1. Now for A equals 2. Now for A equals 2, we get this. So first of all, I'll copy A. That's the matrix A. And then I'll add the B2 here, insert column after, insert column after. And here I'll write a general B2. I'll copy it from the test. B2, 2A minus 4. 6 minus A, and 3A minus 5. So now I'm plugging in A equals 2. So here I get 4, and here I get 0. A equals 2. That's 12 minus 4, which is 8. This is 0. 4 minus 12, which is -8. And here we get 4. Or I wrote -7, -8. That looks like enough. I'll finish writing it, but it seems like a contradiction as well. So the answer is for no values of A is it possible. I will verify with the answers later, but that's what it seems, because my next step will be to nullify the 8 here, and the 4 will not get nullified because of the 0 here. In any case, let me finish writing the question. So that's -8 and is 8. And this is 1. Oh, there are 2 contradiction lines here. So it's enough to do R3 plus R1 to get a contradiction 0, 0, 5. Again, no solutions. That is interesting for bet as well. It makes the 2 sections rather easy. If I didn't make any mistakes, I will check it in a few seconds. But again, no solutions for every A other than 0 and 2, the system has a unique solution. Therefore, there is no case of infinite number of solutions. Now, notice the following. Since forever, if A equals either 0, 2, AX will not equal B2. Therefore, A squared X, which equals A times something, which is AX, will also be different than B2. Thus, first of all, do you agree about that? What do I mean when I say forever? i.e., for every vector x. So A times anything is always different than B2. That's why A squared x, which is A times AX, will also never be B2 when I'm saying never just for these 2 values, 2 times. Therefore, we got the answer for safe bet as well. They're asking us for every value, for which values of A does this system does not have solution. So the answer is 0 and 2. For other values, they have a unique solution. So A squared X equals B2 has no solutions for A equals 0 or 2. Otherwise, there exists a unique solution. Does that make sense? Is anybody with me? Even Sami has gone.
I'm
Tomas,
here.
do you understand anything that I'm saying as well?
It sounds like words. Yes. Yeah.
Do you have any question about the words I'm saying?
I was thinking that if you have a matrix that has a 0 row, you can say that it's not invertible and the multiplication isn't invertible either. So I thought that was the solution for A.
No, but it's not enough. The fact that the matrix is not invertible, it says there is no unique solution. But there still remain the 2 options, no solution or infinite solutions.
Okay.
That's the problem. So this trick allowed me to be sure that there are no solutions, not infinite. Okay?
This is for arbitrary, because X is arbitrary, so AX
Yes.
is X also.
Yeah, yeah, and then what I wrote here, not very mathematically, but I did fix it a bit. But I'm saying that if A is 0, 2, then for every X, AX is different than B2. And then I'm saying that A squared, just because it's A squared, and A squared, it's A times any vector, and it will never be B2. Okay, that's trick. The other possibility was to go like I said I would, but I didn't go the brute solution, calculate A squared, and then solve the solution, the system of equations as well. So first of all, I'm stopping just to see whether that's the actual answer, and I didn't make any the calculation errors.
I
First of all,
only now just realized that that's all your ties behind you.
what's Sammy?
I only now just realized that it's all your ties that are behind you.
Oh yeah, that's
You didn't realize on Sunday?
my big.
No, I just thought it was like a multicolored like thing. Wow, that's crazy.
Yeah, they're all on hooks, and I can simply choose one and unhook it.
How many hooks do you have?
I think behind me are like 250 ties, something like that. I have a few more in the closet, but that's the main event. Okay, so first of all, they use in the solutions the invertible idea. Like I guess they use determinants to find A equals 0 or 2. We did it without the determinant, fine, but we got the same answer. And Gimel, for 0 there is no solution. For 2 there is no solution. So there is never infinite number of solutions. Now let's go back. For 0 to they didn't do the smart thing. They calculated A squared. You see here? They multiplied A. They plugged in A equals 0, then they calculated A squared, and then they solved the system of equation. They found there is no solution. Then they plugged in A equals 2. They multiplied the matrices, calculated A squared, the matrix by itself, and then solved the system of equation and found there is no solution. They went the brute force way, okay, and got to the same answer as me. Both for 0 and 2, there are no solutions. And both for A squared equal B1 and A. But I've shown you why it was clear that when AX equals B2 have no solution, then obviously A squared X equals B2 has no solution. Therefore, solving safe Gimel first is helpful. What about safe Aleph, the first one? It has nothing to do with the others because, like I told Thomas, we do know that A is invertible, but when the constant vector is B1, it's a whole other vector. So still we have the two possible solutions. However, the question is, now I'm reading it and remembering, the only question is whether there is no unique solutions, meaning either infinite or no solutions at all. So great, we need not do any calculation for section A. The answer is A equals 0 or 2, because when A is not invertible, it either has infinite or no solution at all, because there are no 3 bounded variables. In order to get a unique solution, you need 3 bounded variables. You don't have 3 bounded variables. Okay, so I'll write it up, and that's the answer. And for A, and not A, for Aleph, section Aleph, if A equals 0 or 2, there are 3 variables, and therefore A cubed x equals whatever P1 has no unique solution. That's it. That's the answer. I didn't need to calculate A cubed, but I do wish to note that is true since A is a square matrix and invertible. If A is not square matrix, having rows of 0, like I told you in class, is meaningless. But because A is a square matrix, having a 0 row means you're missing a pivot element, and therefore there is a free variable. Let's see the solution they did. Yeah, they use that. They say since A is square, ריבועית, it's invertible if and only if A cubed is invertible, if and only if the system of linear equations has a unique solution. So they say 0 or 2 is where the matrix is invertible. Is not invertible. Yes. Any questions thus far?
Yeah, when you said for A equals 0 and 2, there are 3 variables
Yes.
on A.
On A and on A cubed, or in general,
How do we know there'll be 3 variables on A cubed?
because it's not invertible. Being invertible, meaning that you have a pivot element. If you're a square matrix, that's the point I pointed out in the note here. If the matrix was not square, then it's something else. But within a square matrix, it's invertible if and only if there is no 0 rows, if and only if there is a pivot in every column. So because we know A is not invertible, then A cubed is not invertible, then A cubed has a 0 row in its echelon form, and therefore not a pivot in any column, therefore a free variable. Okay, it's
Right.
fine connection. You probably are able to do it slower currently by the test. Maybe you can do it faster, and if not, you need to think slowly about it. What's the connection between being invertible and the echelon form? And again, because it's square, it has to do with free variables. Okay. They might have learned it as a theorem in class anyway, what they wrote, so but you should be able to deduce it. Okay, next. Let's see if there is within this test there is another reasonable question. Let there be a matrix and let these 3 matrices exist. We know that. We need to find, we can solve it, but I don't love it. I won't do it. Let's not do theory now. Yeah, it's the Colonna test. This was a hard test because there were a lot of cheating, so we made the test a bit harder and then we factored it. I don't know if it worked best, but that's what happened that year. Let's take another year. You and W and base. I think that's nice. I'll do the first question. So we have two subsets of R cubed. U is the set of solutions to the equation x plus y minus z equals 0. What's the geometric interpretation of U? What is the set of all x, y, z such that x plus y minus z equals 0? Can anyone tell? Tomas, are you with us? Sammy, who is talking? Rafael. I'm not hearing you if you're trying to speak.
I'm looking at it and thinking to myself, what? Okay.
You, what is the geometrical interpretation of the set U? The set of, it's a plane, yes, it's a plane.
Mhm.
Okay, the solutions of one linear equation in R3 is a plane. W is also a plane, but it's a bit harder to grasp it now. And I'll skip A, no. Oh, it is subspace W, interesting. Okay, I will skip the first section, but we will answer it when solving B, which is the interesting part for me. So first of all, I wish to write a few things. First, note that U is actually the null space of the matrix 1, 1, minus 1. Do you agree about that? Because
Yes.
U is the set of solutions to the homogeneous system equation that is known to be a subspace, but we're not asked whether U is a subspace or not, and that is a plane. And geometrically, U is a plane. Okay. Now
Sorry.
Yes.
You know it's a plane because it's the null space or because
No,
of
because it's one equation within R cube. That's the very definition we gave to a plane, to be honest.
Okay.
Other way to view it is to go to find the base, find the span, and see there are two vectors there. It's not really it doesn't really matter, but I think it's helpful. Now let's look at W. W is more interesting. Why? W is the set of all vectors such that the x is 1 plus t, the y is s minus 2, and the z is s plus t minus 1, such that s, t are real numbers. Okay? Now, let's separate it like I did before. So we get here 1 minus 2 minus 1 plus t times 1, 0, 1 plus s times 0, 1, 1. Now that's a bit of a trick question. Is that a span? Is W a span of vectors?
No,
Why not?
because we can make the first vector by doing t equals 1 and s equals minus 2.
that does not answer why is it not a span.
Because it's not linearly independent.
That's not a reason not to be a span. It's also the wrong answer in general, but
It's an attempt.
actually, the reason you gave me answers why it is a span, but it's a bit more complex to understand why. What I'm asking now, when I wish to emphasize it, when we had something similar a long time ago here, right? We've seen that the null space of A cubed is some scalar times the first vector plus some scalar times the second vector plus some scalar times the third vector. So that is a span because we take all general linear combinations. What's the problem here? The first vector is just multiplied by 1 and no other scalar. So that is not clear because we are not allowed to multiply the first vector by any scalar we wish. And yet, we can prove that W is indeed the span of only these two vectors. But that is not trivial. It's not trivially true because I just ignore this vector. The reason that I am able to is because of what Thomas said, because I can create this vector using TNS, therefore it can, I don't know, hide within TNS in a sense. But the way I will prove it will be implicit or using a bypass. You will see. Okay. W is given to us in a geometric form, but in order to find the intersection, we rather have the algebraic form. How do we get it? I think I did it once in class. I'll remind you again. XYZ is contained within W if and only if there exists A and B, let's use the same letters, S and T, such that XYZ is equal to this. Agreed? The vectors within W are exactly the vectors of this form, that there exists some T and S that creates them. That phrasing of the problem gives rise to a linear set of equations. If and only if there exists T and S such that X equals 1 plus T, Y equals S minus 2, and Z equals S plus T minus 1. meaning the following set of equations in S and T has a solution. And let's look at the לואי, אולי תפסיק כבר להיום. מה זה לא אתה? אז מי אתה? זה רוח רפאים? זה אתה. אתה מפריע לי ללמד. לך למיטה. לואי? לא לשלי. Just a second. לואי? לך למיטה שלך עכשיו. בסדר, לך למיטה עכשיו. לואי, יש לי עוד 3 דקות לשיעור, אתה מבזבז את הזמן, לך למיטה מיד. It doesn't feel like going to bed to be punished. Okay, so t must equals x plus 1. S must equal y plus 2. And lastly, s plus t equals z minus 1. So let's put it in a matrix. Put it as S T, and we have 1. S is the first or T is the first? Whether it really matters, but T is the first. Let's do T. So 1, 0, x plus 1, 0, 1, y plus 2, 1, 1, z minus 1. We'll Gauss eliminate. I'll do it quickly in my head because we don't have a lot of time. I'm removing the first 2 rows from the third one. And then we get z minus x minus y minus 4. And then we say, so there exists a solution if and only if there is no contradiction, meaning z minus x minus y minus 4 equals 0. Thus, Lennon, אני בשיעור. Thus, W is all the x, y, z such that x plus y minus z equals minus 4, if I'm not mistaken. It's double negative. X, oh, and this is really nice. So first, we see it shouldn't have been 4, you know? I made a mistake here, I think, because that is not a subspace.
I think
I
it's
made
3.
some. It's not supposed to
no.
be 3. It's supposed to be 0. Let me make sure where did I make a mistake, because they claim it is a subspace. That is not a subspace because 0, 0, 0 is not contained with it. So I must made some mistake. And I'll take a few more minutes of your time. X ought to be 1 plus t. X ought to be 1 plus t. So if x is 1 plus t, t is x minus 1. Maybe that's the only mistake I did. Yeah, I think that's enough. I think that is enough. Because here I get x minus 1. This is x minus 1. And now the third row minus these 2. So it's minus 1. No, still not great. Y is...
You need it to be minus 2 as well.
No,
No.
because y is s minus 2. When I move it to the left-hand side, s is y plus 2. I wasn't wrong about that.
You just wrote
That's-
it down. You just wrote it down wrong.
No. This
That
is
one,
plus. This one, not the y. The y is fine, the z. Oh, that's what you said? Whatever.
What?
So now, finally, it actually works. 1 minus 2 is minus 1, minus 1 is 0. So here we get nothing, and here we get that. Great. So it's 0. And first of all, we see this is a subspace since W is the null space of the matrix 1, 1, minus 1. And can anyone notice what's the connection between W and U? Look at this. And look at that. It's the very same space. So the intersection W intersection U actually equals W and U, and it's easy to find a base. That's what I asked, right? And it is easy to find bases for the null space. I won't do it because I'm out of time. But this trick solved everything quite fast. So that's enough for today in linear. At 4 o'clock, we'll meet at the same link for calculus, unless there will be shootings from Iran or Yemen or Gaza, Lebanon, Syria. Either of these may cancel the
Cyprus.
Cyprus. Yes, the United States, who knows? Okay, yes. Have a good one.